Hi, I'm Stephen Lund. I'm a motion control specialist with Werner Electric Supply.
Today, I'm going to show you how to use Motion Analyzer Online from Rockwell Automation to size and select the appropriate servo drive and servo motor for your application. This is online, so you need to use an internet browser. I use Google Chrome. So I'm going to click on Google Chrome. I'm going to type in motionanalyzer.rockwellautomation.com. If you do not already have an account created, you'll need to create one. You can do that up here. I already have one, so I'm going to log in. From this page, I can browse products from Rockwell Automation. Here I could navigate to a particular drive or motor based on part number that I was interested in, and I could download 3D models. I'm not going to worry about that right now though. I'm actually going to go into my library where I have an existing project created, and I'm going to navigate through and explain to you how I did it. So I'm going to click on Library. I'm going to go to example B. First, I'm going to show you if I wanted to share any of my projects here in this list with other people who have accounts created, I could go to Action and click Share, and I could enter in their email address here, and I could share this project with them based on if I wanted to let them read it, access it, or even edit it. So I'm going to click on example B. That's going to bring up the navigation window for the entire project. So here you can see I have architecture overview. That's where I'm at right now. It's showing all the axes in this project. I have my preferences that I could set up. I have my power analysis, which I'll do later to determine the correct power supply. And I have my bill of materials. When I'm all said and done, I can see exactly what part numbers I need to order for this project. First, I'm going to go to axis 1. Since I don't have any designation for the type of motor, that means that this axis is not complete. You can see by the X's there. So I'm going to click on Edit. And now you'll see this navigation pane across the top. And that basically shows you the different steps of sizing that are either complete or incomplete, and also gives you the ability to go to any step in the process to navigate that. This application was a linear application, so I clicked Linear, and I'm going to continue to Profile Editor. Let me go back. Start that over. So across the top here, you can see that there's a navigation pane which allows me to go to any point in the process of designating the parts and pieces for this application. So if I wanted to, once I was complete, go back and edit any of the parameters of the gearbox, for example, or the drive, I could do that. Right now I'm in the Setup tab, which basically I get to determine whether or not it's a rotary or a linear application, or even follow an application template. So if you have really complex motion applications that are kind of like a winder, unwinder, or pressure roll feed, and you're not quite sure how to enter in those numbers, you could click any one of these application templates, and it's pretty easy to follow. For today's application, we're just doing a simple linear application that has a couple of components and make it easy to demonstrate. So select linear and continue to Profile Editor. Once it's done loading, you can see the profile I've created here is a trapezoidal profile based on the velocity. It's a linear ramp in velocity to a dwell in velocity down to a decel in velocity. That, of course, is incrementing my position by a set amount that I've entered in. I think, let's see here, let's click on that. Yep, I'm going 4876.8 millimeters in 5.333 seconds. That's the designation for this trapezoidal move. And then I have a dwell of 2 seconds. So going back to this, if I wanted to add a load in this particular segment, say for the rest of the machine cycle, I don't have a 5-pound box sitting on this linear mechanism, but I do during this move, I could add a segment load here. And down here under segment loads, I want to add a 5-pound box just for that segment. I would enter it here and be done. So now you can see that I have that 5-pound box. Get rid of all these other ones here. You can see that during this segment, I have that 5-pound box showed. load mass 5 pounds on this segment. But then here, I do not have that 5-pound mass. It drops down to 0. And because I don't have that load mass here, I can't edit it here, it's updated at 0. So that's how I could add a segment load. If I wanted to add a force or a load that was for the entire operation of the machine, I could do that here under the Add tab. And I could add a mass for the entire or a variable permutation of the entire application. So I'm going to choose constant, do 5 pounds again, click apply, and there we go. I have this additional load. It's a 5-pound mass, and it's right here going all the way across. To go back to edit the profile, if I need to edit again, I would click under the motion tab, click edit, click on the segment that I want to edit, and here I go. I can change the acceleration profiles and the velocity profiles. You know, right now it's just trapezoidal, it's linear. I want to change the jerk percentage to decrease the third order derivative, so I don't have bottles tipping over around a corner or something like that. I can make that profile more demanding, but I'm going to drop that back down to 0 and leave it alone. But that's where I could change those. Okay, so now that I've selected the linear motion profile, everything's set up, I have my load masses, I'm ready to go to the next step. Scrolling up, my next step is a custom mechanism. So when you go to the custom mechanism tab, you can choose between a lead screw, belt drive, chain sprocket, rack and pinion. I've chosen a belt drive, and down here I've entered in the parameters of that belt drive. I've added a table mass, I've added a belt mass, I've added a diameter of the driver. If you look in the diagram here, the driver's right there, and the diameter of the idler group 1 is right here. I have 4 rollers in this application, so I'm accounting for that here, entering 4 under the idler. I've added some friction torque, and I've calculated inertia in kilograms centimeters squared. If you didn't know what the inertia was and you wanted to calculate it manually, you can pop up this inertia tab. So if you wanted to calculate the inertia for an idler or a pulley, you would click on this calculator. It would bring up this window, an inertia calculator window. And for example, for an idler or a pulley, you have a hollow cylinder, right? Because you have the outer diameter of that pulley, and then you have the inner diameter where the shaft goes through that pulley. So I'm going to choose a hollow cylinder. I'm going to choose a material of steel. There's a bunch of different materials that you can choose that determine the density of the item that you're selecting. But I'm going to choose steel, and you see it gives a density of 7,900 kilogram meter cubed. So my outer diameter I could say is say 100 millimeters, and the width is 25 millimeters or an inch, and the inner diameter is same thing, 25 millimeters or an inch. That calculated my inertia here, and I could take that value and I can come over here, and you know I've taken that value and done a control V. I can come over here and put it in and do a control C with making sure that I'm maintaining units. So this is kilogram meter squared. This defaults to kilogram centimeter squared. So I want to change that to kilogram meter squared, and then I could copy paste that value in. But I don't want to do that. I want to keep what I had here. So now I've entered everything in. I've got my inertia values. I've got all these tables populated. I've got belt mass, table mass. Everything's accounted for this conveyor. I'm going to continue to transmission. And at this point, just for sake of adding one, I'm going to add a belt drive. And I'm going to do a one-to-one transmission so it doesn't really change anything on the application. So once it generates here, it's going to pop up into this area. All right, I've got a ratio of 1:1. Ratio is 1, efficiency 100%. And inertia, same thing. I could pop up this inertia calculator, calculate my inertia of that pulley, copy and paste it into this little editor, and click apply. So now I've got a transmission. Next step is to go to gearbox. You can see how I'm navigating across the top here. If at any time I wanted to go back and change something, I can. I just click one of these selectors. So for gearbox, I already have one chosen. I have the CVH series from Wittenstein chosen. If you wanted to choose a particular family, you could click on a family. So now I clicked this and it generated that. So when I do a search, it's going to include all of the CP gearboxes from Wittenstein as a selection to determine the best solution or best fit. I'm not going to do that today. I have a particular part number chosen that I'm happy with. If I wanted a different style and I wanted to filter it out because I'm not quite sure what I wanted to do, I could come over here and do gearbox filters, and I could choose, planetary, worm, helical. I could choose a different manufacturer. I can do a configuration series from any of those manufacturers, and I can just basically filter out anything that I don't want to look at and only look at what I want to. And that's important because when you do your solution search, the more options you have the algorithm looking at, the longer it's going to take to come up with a solution. So the more you can narrow it down and do your pre-work before you get to that point, the easier it's going to be. So I have this particular gearbox selected. It's a CVH 63SS, ready to go. It's all entered in, selected gearbox. So I'm going to continue to motor. And here is just a formality. Are you trying to enter in a user-defined induction motor or a motor that's prepackaged and already selected and has the parameters in the motion analyzer? Most likely you're going to choose this. So I've selected motors. I'm going to continue to select motors. Now again, here I have a selected motor already input. I have a VPL B1153 Echo. Now if I want to choose an entire family of a motor because I wasn't quite sure if that's the one I wanted to use, or I wanted to see some of the options of motors that were similar to ones I've already used so that I could keep my parts list low, I could do all of that. I could either choose a family, by selecting the entire family, or I can enter in a part number manually here. Same thing as before. I can filter out by, IP ratings, certification, environment, induction motor, parameters, force ratings. All that stuff is selectable to filter out and make your selection process as simple as possible. But I have a motor selected, so I'm going to go on to drive. And for this demonstration, I'm going to do the Kinetics 5700 since that's our flagship offering right now. It's the first one on the list. I have entered in my power requirements of 483 phase. I actually have a drive selected that's appropriate for that motor. If I didn't know which drive I wanted to use as far as a 5700 or even a 5700 but what frame size, I could just enter in the family like all the other ones, and that would search all of the drives available in that family and see which ones were the best solution. So at this point, looking through the chronological steps here, I have everything selected and I'm ready to do a solution search. So at this point, I would do a search. Once this button turns green, it's going to search through everything that I've had selected, which is already pre-selected, and it's going to come up with that solution and show me how compatible that is and what the ratings are. So clicking on analysis, I can see, all right, I've got that VPL B1153E. It's got a 20:1 ratio. I'm using this drive, and these are the usage values for that motor and that drive. So I can see that my compatibility is good. My bus utilization is only about 60%. I'm not anywhere near 50% on any of the other drive parameters. My speed's good, it's about 65%. Torque is good, it's only 30% of the capable torque of the motor. I'm ready to go. Same thing with the gearbox. On this left-hand side, I've got a torque speed curve that's showing me my basically like when it's operating, what's the nominal values for that motor and its capability, and what are the peak values for that motor and its capability. And all the key points of the profile, everything is below the nominal value. Even the peak forces for that particular profile are also under the peak limit of that motor. So this is a really good solution. I'm not operating up here in this area, and so it's sized appropriately. I could go through and individually look under the drive, like, okay, what's the application demanding? What's the drive capable of? Same thing for the motor. What's the application demanding? What's the motor capable of? And of course, same thing for the gearbox. All these parameters are input and does the math all for you. what is the application demanding, and what is the gearbox capable of. So now that's all selected. I could basically go through here and say these part numbers are all good and ready to go, and then find the user manual and verify part numbers and create a bill of materials. If that's not something that I really want to do, and I wanted to actually input it into here and save it for like maybe demonstrating to a customer the parts that were selected, I could go to configure components. And at this point, there's really no configuration options for the gearbox because you already have it selected in the part number. But there are some configuration options for the motor and the drive. So I'm going to click on motor. And here I can choose whether or not it's a keyed shaft, if it's got a brake, if it's got a shaft seal, any of those options. I could also download the motor model from this page. So I'm going to say that I'm going to want a multi-turn absolute feedback type and no brake keyed shaft. So if I come down here, I see I've got a keyed shaft, I've got no brake, I've got no shaft seal, and I'm multi-turn absolute. So I'm going to select that and watch on the left-hand side how it sets the configuration for that motor. All right, now I have a set configuration. So this is important to select the appropriate type of encoder and shaft seal and brake, because that's going to dictate the type of cable that you use to connect the motor to the drive. So now that I've selected and set the configuration for the motor, I'm going to do the same thing for the drive. You only have two options here. You're either doing safe torque off over Ethernet or hardwired with the ERS3 module on the 5700, or you're doing advanced safety features. Since we're not going to be even delving into that, I'm just going to choose the ERS3 no advanced safety. So now that that's selected, this little thing pops up and I'm able to choose a cable. Typically I do 9-meter cables. It's a single flying lead connector type and it's continuous flex. I click add and that adds it to the list. I'm ready to go. Everything's configured. So now if I click on the details for that axis that I just edited, you can see that I have a particular motor selected, I have a particular drive selected, and I'm good to go. So now you can see when I open that up, I've got an actual configuration set for this axis and everything is good to go. I have a particular motor selected, particular drive selected, and now I need to figure out, especially for a 5700, what power supply I want to use. So first thing is that these axes are small enough that they can reside on a dual axis module. So I need to basically group them together so that I have one dual axis module with two motors and one power supply to power that dual axis module. So I'm going to click on merge. Here I'm going to select the other axis. I'm going to click merge. And there, I'm all selected. Now you'll notice that even though it was the same drive size, the actual designation for the type of drive is irrelevant when doing power sharing. So even though I have an ERS4 here, and I did have an ERS3 selected for axis 1, and I had an ERS4 selected for axis 2, when I did the merge, it automatically upgraded them both to ERS4 because I went with the safer version. So now both motors, because the need was for an ERS4 advanced safety on one of those axes, I have to choose that ERS4. And then I'm going to use the second axis as an ERS3. It's basically not going to have advanced safety. So it automatically, for you, smartly defaulted to an ERS4 since that satisfies all the conditions needed for this particular application. So now they're merged together. Both of those motors are going to be on the Kinetics 5700 dual axis drive, and I'm ready to select a power supply. So at this point I'm going to click power analysis, and since I only have one dual axis module, I only have one shared bus, which is the one dual axis module, and so it's automatically selected here. If I had more axis modules and I wanted to share that bus, I could click edit and add those other axis modules onto the shared bus and click save. But don't have that going on right now, so just doing the dual axis module. Get out of that window, and it's automatically going to do a search to say, okay, you've got these two motors, they're running at a certain rate, they're on this drive, what power supply is the best one? If you're not confident with the automatic cycling, you can do an auto configure, and that will redo the request. And it basically goes through the motion profiles and goes to like worst case scenario for current demand and figures out which power supply is the appropriate one for your configuration. So you can see here it's selected the 2198 PO31. It's only using 9% of the converter utilization capability, and it's only using 9% of the peak power utilization. And I don't need a shunt. If I needed one, it would automatically select that here. If it didn't populate, you could redo it or do it manually. So now that's all set to go. I have selected my motor, my drives, I've done my power configuration, I have my power cables between the motor and the drives. I'm good. So now at this point, if I want to see what that bill of material looked like, I can just click bill of materials. It should generate here, and you'll see that I have axis 1, axis 2, and then accessories that I need. So I have my power supply down here, I have my different motors selected for my different axes, I have the one dual axis module drive, and then I have my gearboxes selected. So at this point I could export this BOM, and it exports the entire bill of materials to a CSV, and you could shoot that off to your inside sales rep or put it into Proposal Works and generate something like that, or even integrated architecture builder. So now you have something to work with for this particular project. Okay, so that's it. That's how you size and select parts and components for a servo application with Motion Analyzer Online from Rockwell Automation.
If you'd like to learn more about Motion Analyzer Online, feel free to contact your local rep or me at Werner Electric Supply.